Hello and welcome to this edition of our global webinar series. Today's topic is Component Basics, Tantalum Capacitors. My name is David Adib and I am a Senior Technical Marketing Engineer here with KEMET in Florida, and I will moderate the webinar today. We are very pleased that you find time to join our webinar. Our presenter today is Sam Accardo, our field application engineer. With this information, I hand it over to Sam. Hi, Sam. Thank you for your time today. Please tell us a little bit about yourself before you begin your webinar. Thank you.
Thank you, David. Hi, everyone. My name is Sam Accardo. As David mentioned, I am a field application engineer at KEMET. I currently cover the northeastern United States, which is the Virginias all the way up through Canada, and I also cover eastern Canada as well. Brief about me, I've been with KEMET for about 3 years now. I joined straight out of school from Louisiana State University, where I have a degree in electrical engineering and a degree in mass communication. So for today's webinar, we do have a pretty large agenda, so we'll just hop right into it. So today we're going to be covering the design of tantalum capacitors, the materials and processes that we use to manufacture them, or to make them at least, some of their characteristics, their applications, reliability models, strengths and weaknesses by dielectric, and then we're going to go into a product alignment to tell you a little bit about what our focuses are for each, market segment. So starting off, I guess it's best to explain what type of capacitor a tantalum capacitor is. So there's basically two types of fixed capacitors. There's non-polarized, which means that they could have reversed bias, which means that they could see AC signals. And those are typically going to be film capacitors and ceramic capacitors. Take it that class 2 and 3 dielectric ceramics don't do too well with ripple currents and stuff like that. But there's also polarized capacitors, and polarized capacitors cannot see reverse biased. And typically in our data sheets, we specify that they can handle a certain amount of reverse bias for a short duration, but it's not going to be something up to something like the rated voltage. So polarized capacitors, for the sake of this argument, should not be used in any reverse biased applications. And those types of capacitors are going to be supercapacitors and electrolytics. And I know a lot of people are probably thinking, well, isn't tantalum not electrolytic? Isn't aluminum electrolytic? Well, the answer is both of them are technically electrolytic capacitors. And at KEMET, we offer solid tantalum capacitors. So there's solid, there's non-solid. Non-solid is wet tantalum, while the solid is conductive polymer and manganese dioxide, or MnO2. And today we're going to be talking about the conductive polymer and the MnO2. So starting with the design, looking at the construction of the capacitors themselves, as you can see here, we have two typical constructions that we use at KEMET. And the first one is the standard package. As you can see, it's a kind of a larger profile type device. It has a glue pad on the bottom, and then it has a larger lead frame that kind of comes up halfway up the device. And then we have what we call the face down package, which is basically parts that come in similar type footprints, except they're, I guess the best word is more volumetrically efficient. And we'll get to why they are more volumetrically efficient in just a minute. But what you notice is that the front end and the back ends of the capacitors don't have the large lead frame coming up on them. So this is a bottom view of the face down package, and this is the bottom view of the standard package. Now, looking at the construction of the standard package itself, this diagram you could typically find in most of KEMET's data sheets. So if you are looking at a particular type of MnO2 or polymer and you want to know what the construction looks like, check out the data sheet. It's usually towards the end. But what you see here is that we have a tantalum wire, I guess right in the middle, and then we have a tantalum pellet or multiple pellets that have been compressed and centered around that. Then we have a layer of tantalum pentaoxide, which is the dielectric layer, a polymer or an MnO2 in some cases. a carbon layer, and then a silver paint layer. And this particular element, this capacitor element, is basically placed inside of this packaging. We essentially weld a lead frame onto the wire, and then we use a silver adhesive on the bottom of this lead frame to attach to the top of this capacitor element, and it's placed into this packaging. And what you'll notice from this packaging is that there's a fair amount of unused space within this, this packaging. So what we've done is we've created the face down package, which uses the same general idea for the capacitor element itself, except for this time we actually weld a smaller lead frame directly to the device. And then we also have a smaller lead frame coming directly off the bottom of the capacitor. And what that gives you is a much more volumetrically efficient device. So if you're looking at a standard package and a face down package with the same case sizes, so 7343 by 3.1 millimeter height. Then if you're looking at the same two parts with the same voltage ratings, you're probably going to be looking at a higher capacitance in the face down package, because we could fit more of that capacitive element within this one device. And then also I mentioned earlier that the standard package has a lead frame that kind of goes halfway up the outside packaging. By eliminating that, we're actually lowering the ESRs or the ESL as well, because lead frames give you parasitic inductances, and by using these smaller lead frames, we're able to eliminate, or not eliminate, but lower that ESL as well. So that's another benefit of that package. Now, looking at the general construction of a polarized capacitor, on the top left, you see that we have an anode and a cathode, which are the positive and negative electrode terminals, and then we have a dielectric. For a tantalum capacitor, the anode is a tantalum metal, the dielectric is the tantalum pentaoxide, and the and then the negative electrode, the cathode, is MnO2 or polymer. And the way that we figure out the capacitance based off of essentially a standard capacitance formula that's pretty much the same for pretty much every type of capacitor out there, whether it's ceramics, electrolytics, the tantalums, the films, whatever it may be. There might be some slight variations, but for tantalum, we're looking at the capacitance being equal to the dielectric constant, which for all tantalum is 27. We're looking at the permittivity in the vacuum, which is epsilon naught, and those two are essentially constant. So when you're looking at the capacitance of a tantalum capacitor, it's essentially going to come down to two things. One is the area of the conductive plate material, which is going to be the tantalum pellets, and then we're also going to be looking at the dielectric thickness as well. And just a reminder for those of you who have probably attended our MLCC presentation, and I guess just maybe new information for everyone else, the dielectric thickness also is what we help determine how much the voltage rating of the part is going to be. The thicker the dielectric thickness is, the higher the voltage rating. So by this formula, the thinner it is, the higher the capacitance is going to be. So they kind of go hand in hand. We just need to make sure that we're looking at the right parts. So moving on to like the construction again, we have essentially a tantalum wire that has been compressed, or not a tantalum wire. We have a tantalum wire with tantalum pellets that have been compressed and centered around it. And it makes essentially the devices that you see here. And this is the base for the tantalum capacitor itself. And what you see on the left-hand side of the page now is essentially the interconnected tantalum particles after they've been pressed and centered around that tantalum wire. And then essentially, to give you an idea of what they look like, we have the tantalum wire with the interconnected tantalum particles. And then on top of that, we either deposited the MnO2 or the polymer, and then we have a carbon ink, and then a silver paint. And then that is essentially what makes up the capacitor itself. Remember on one of the previous slides, I talked about the construction, which is the anode, dielectric, cathode. The left-hand side is essentially what it looks like as a drawing of what it could visually look like. So we have the interconnected tantalum particles, we have the dielectric, the tantalum pentaoxide, And then we have the cathode material, which is either going to be the MnO2 or polymer. And we're going to get into a little bit more detail on each of these in just a minute, but just want to give you an idea of the construction of those parts. And then one additional slide just to show you kind of what the packaging is like on the standard tantalum capacitor. On the top left, you could see that we have the anode itself, which is or the capacitor element that has been dipped in a silver, silver, basically dipped in silver itself. It has a tantalum wire that's coming out of the anode itself, and that has been welded to the lead frame. The negative lead frame has been connected by that silver epoxy that I mentioned on a previous slide, or not epoxy, but an adhesive. On the top right, you could kind of see what it looks like when you turn it over to its side. The lead frames are coming straight out. We put this device into into its packaging, and then we essentially build them, or not build them up, but fold them up, and then flip this entire capacitor upside down. And that is the construction of the standard design part. And just to go back to the volumetrically efficient face down package, as you can see here, there's a pretty good amount of space inside of this capacitor or inside of this packaging that isn't being used. So that goes back to the volumetrically efficiency of that face down package. Now, a little bit about the materials and processes. Starting with the tantalum itself, by the way, KEMET is the world's largest user of tantalum out of anyone in the entire world. And also our processes are vertically integrated, which means that we have 100% conflict-free material that comes out of the Congo. We have a partnership with them. We've built them schools and hospitals, and we get conflict-free material from them. So we should not ever have another shortage like the early 2000s for this type of material. But a little bit about the material itself, and then just to, I guess, go back to the vertically integrated, we also have our own blue powder company, which makes the pellets for the tantalum from the tantalum ores that we get from the Congo. We have facilities in Mexico that do and not just Mexico, but also in China and Asia that do the manufacturing. So we're almost 100% vertically integrated from start to finish on these parts. So that's a very good thing when it comes to KEMET. So starting off with a little bit about the tantalum itself, it's element number 73. It's TA is its periodic name or number. And starting with the ductility, that is basically its ability to stretch under tensile strain. It also has a high corrosion resistance. It has a very, very high melting point, 3020 degrees Celsius. It has a high resistance to heat and wear, and it has high biocompatibility. And a fun fact, when you're looking at the applications on the right-hand side, under medical, tantalum is not rejected by the body. So it's used very often in things like joint replacement, skulls, plates, screws, clamps, and wires. So it's good in bodies, but also the material is used in a lot of different types of devices, whether it's electronics, optics, super alloys, and it's used in high temperature applications as well. So these types of devices are used in all kinds of applications. And the fact that KEMET is the world's #1 user of this product just makes it a little bit more special for us. Now, looking at the tantalum pentaoxide, that's the dielectric itself. One thing I mentioned earlier is that the dielectric constant is only 27. 27 is actually very low when you compare it to other types of capacitors. But essentially the tantalum pentaoxide could be grown at very thin thicknesses, and that is where we get, and not where we get, but that's where we get most of our capacitance, our CV values, our capacitance values. These parts are very volumetrically efficient in part because of that. But the key thing here is the dielectric breakdown, which is 470 volts per millimeter, which means that these parts could have very thin dielectrics, but also very high voltage withstanding capabilities. So if you look at the chart on the top right-hand side, you'll see that there are a few different voltage ratings here that we're comparing 2, 4, and 6 volts for tantalum and MLCCs. And as you can see here, The tantalum parts is anywhere from 20.7 to 36.8 nanometers of a thickness for each of those ratings, while an MLCC has to be at least 600 nanometers to have that same voltage rating. So the tantalum pentaoxide is a very robust dielectric, and it's capable of handling higher voltages per thickness or per nanometers of thickness or millimeters of thickness as well. So it's a very good dielectric for that. Now, looking at the formation of the tantalum pentaoxide, essentially we have a tantalum pellet or tantalum pellets that have been compressed and sintered on a tantalum wire. And essentially you could think of the picture right in the middle, the before formation. That's essentially what it would look like, or just an individual pellet that is. And when we put that part in an electrolyte and apply a formation voltage, by the way, is basically a voltage that we apply that'll correspond to the rated voltage of the part. When we apply that formation voltage, the tantalum dielectric or the tantalum pentaoxide is going to grow 1/3 of the way in and 2/3 of the way out. And so what you see on this screen is basically the original pellet size. And you could see that the pellet itself is now a pretty good amount smaller. It's 1/3 of the way in smaller, but also you will notice that it grew out. So this very faint line right around the outside is basically showing us um, where the original tantalum pellet was. And as you can see, it did grow in a bit, but it also grew out quite a bit. And what that leads to is this overview of basically what it looks like. So what we have here is a 4x4, so it's essentially 4 particles, 4 necks, 1 pore of particles, interconnected particles. And when we apply the formation voltage, what we see here is that the necks get smaller, or the internal necks get smaller, and you can kind of see them here. The original neck was quite large here. The pores have gotten smaller, and by the way, whenever the necks get smaller, uh, that's not a good thing, because the smaller the neck, the smaller the higher the resistance of that part is going to be. And then the pores being smaller isn't a good thing either, because essentially that's going to cause inefficiencies when we start coating the part with either the MnO2 or the polymer. So we want the pores to be as large as possible. We want the necks to be as large as possible, but we also want the dielectric to be thick enough to handle whatever voltage we're looking for. So what we see is when we're looking to at the formation, we see here that we have a very large neck, we have a pretty large pore, and then we do the formation. What we see here is that these pores have gotten, or these necks have gotten smaller, the pores have gotten smaller, and in some cases, some of these particles are lost, which means that there's a loss in capacitance with all of the particles that essentially did not, or that essentially where the dielectric grew through the necks. So we want to eliminate as many of these eliminations of necks as possible. We don't want to have these necks grown through. We want to make sure that they're connected. We want to make sure that they're as large as possible so that we could have the lowest resistance possible. And then we want to make sure that the pores are as large as possible as well so that we could coat them with the MnO2 or polymer. And what you see here is basically a image that was taken that shows a small neck of a tantalum and then how the dielectric is formed through the neck. And then you could also see on this side over here the differences in the tantalum particles. What you see is the 50K powder and the 150K powder. The 150K powder has smaller tantalum particles. And by the way, the smaller the tantalum particles, the more capacitance you're going to have. But also the lower the voltage rating is going to be. If you think of something like a soccer ball has a very large surface area. But if you think of, let's say, some marbles, and you place and you measure the surface area of a marble, and you place a bunch of them inside of the soccer ball, you're going to notice that the area of each of the marbles added up is going to be much greater than the area of the soccer ball alone. So the smaller that we go for these tantalum particle powders, the higher the capacitance is going to be. But again, when we start applying those voltages, the smaller the particles already are before the formation, the smaller the necks are going to be, the smaller the pores are going to be. So that's why these parts are going to have smaller rated voltages. So we have to take a lot of care in picking out what particles we're going to use, what tantalum powders we're going to use, and then what the formation voltage of those parts is going to be. So that's a little bit about the dielectric. And then looking at the cathode itself, we have to, when we're choosing what cathodes, in particular, we've chosen MnO2 as the original cathode, and then more recently the conductive polymer. There's a few things that we have to consider. And the first one is the ability for it to impregnate the pores. If it's not able to do that, then we're going to have inconsistencies and we're going to have problems with the part. Also, the cost, we don't want to use something that's going to cost a lot of money to put in. One of the other things that I want to mention is the high conductivity. There are materials that are probably much more conductive than polymer or MnO2, but the problem is that they're going to cost more and they probably won't be able to impregnate those cores. So we have to consider how conductive the two parts are going to, or that cathode material is going to be. And as you can see here, the conductive polymer itself is going to be far more conductive than the MnO2 is going to be. And that's going to give it a number of benefits, which we'll go through this presentation. But there's one additional thing that we have to look at when selecting the cathode itself, and that is its ability to form a non-conductive plug in the dielectric. So not with the KEMET and with other manufacturers, we all manufacture tantalum capacitors with faults in the dielectric. It's just how they're manufactured, and the ability of the cathode to essentially go through joule heating, which is the ability or taking the part and heating up, for instance, the MnO2 to a certain temperature so that it becomes Mn2O3 and form a plug. So its ability to form a plug and lower the leakage current of the device is also very important. So moving on to the characteristics, I know we have 10 minutes left, so I'm going to speed it up just a bit. Talking about the characteristics of tantalum, there's a few reasons why we've chosen it. The first is it has a stable capacitance. When compared to something like a ceramic capacitor, particularly a class 2, they have the DC biased effect, which is as you apply voltage, the capacitance drops off. And also there is a change in capacitance over temperature. Tantalum does not have that. Tantalum also has a stable leakage current over time. It's higher than most other types of capacitors, but it's stable over time. They also have high reliability, and the failure rate decreases as you derate the device. They have very long life, and most of the time it's going to outlast anything else on the board. And then it's also the most volumetrically efficient type of capacitor on the market. So you're going to get the highest CV values that out of any capacitor in similar case sizes. Now, one of the effects that we have to consider is the RC ladder effect, which basically leads off to the capacitance roll-off. What you see on the top left is essentially the internal design of the part, and we have the interconnected tantalum particles with all of the different capacitances of each of these elements connected by a series resistance. And that is basically going to have the same type of features as an actual RC ladder, which is where we have a resistance capacitor, and that's building a network all the way through RN to CN at the end. And so the way this works is that at lower frequencies, let me start off and back up and just clarify one thing, that resistance of a device is going to increase with frequency. So as you go up in frequency, R is going to increase, and that's going to be R1 through Rn. All of them are going to start increasing. So at lower frequencies, this device is going to act exactly as it should. The RC time constant of each of these devices or each of these interconnected particles is going to be the same. But as frequency starts to increase, what we're going to see is that the particles or the CNs and the RNs are going to start going up, and the CNs at the end, or the furthest away from this rise wire, are going to start increasing, or being not increasing, but all of these are going to increase, but the ones that are at the end are going to have a time constant that is going to be above what the frequency is going to be. So what I'm trying to say here is that as frequency increases, we're going to start seeing a loss in capacitance up until the point where only the interconnect to be working. So you're going to have a very fast and quick drop in capacitance. And we could actually see that on this next slide, where we have 3 different types of similar polymer capacitors with different ESRs. So we have 35 milliohms, 70 milliohms, and 9 milliohms. And what we see is as frequency begins to increase, and due to the RC ladder effect, that capacitance starts to roll off, and then it starts to roll off very, very quickly. So within a very short frequency range, you could be you started off. So what that means for us is that these types of capacitors are typically used in applications that are less than a megahertz, because anything above that, you're going to start losing the capacitance, and you're not going to have that retention. And that brings us to our next point, the applications of a tantalum capacitor. Typically, that's going to be filtering, decoupling, and holdup. They're used in these applications because one, they're probably the most, and not probably, they are the most volumetrically efficient capacitor. So when you're needing higher capacitance values, and when you're needing a smaller device, you're going to be highly reliable. So they're used in a lot of different applications, whether it's automotive to military, commercial grade products. They're used in a little bit of every one of these application places. And then, of course, these parts are also used in a few different locations. So in particular, if we're looking at this graphical signal of USB, it might be a computer or something like that. What we see is that we're using the tantalum capacitor on the input of the DC to DC converter, which is typically decoupling. We're also using it on the output of those converters, which is typically for filtering, and then also on the input of the other converters, which is typically also could be used for decoupling as well. And then on the very output of this converter, they're used in filtering. And so they're used for decoupling and filtering very often, but because of their high volumetrically efficient, they have high charges. They could hold a lot of charge in the device itself. They're also used for hold up applications as well. And what you see on the bottom left-hand side is a range of where the capacitor falls for capacitance values over voltage. And then I guess one of the final things I wanted to say is based off of decoupling. On the previous slide, I mentioned how there's a very quick capacitance roll-off frequency approaching a megahertz. So typically, these parts are used in conjunctions with other technologies, in particular ceramics for decoupling applications, because you want to, if you have a target impedance and a target frequency, you want to be sure that you're using a wide range of different types of devices that are going to push down those impedances at certain frequencies based off of the application. So the tantalum capacitor does very well at frequencies lower than a megahertz for decoupling applications. Now, looking at the reliability model, the first thing I want to point out here is that the reliability model that we have, which is also stated in the datasheet, is based off of leakage current. We're defining the end of life of these parts based off of leakage. And what we've done is we've taken the category voltage and temperature, which are the rated voltages and temperatures of the device that's specified in the datasheet, as well as the minimum test time, which is also stated in the datasheet. And we essentially combine those or multiply those together using a few equations, using the application voltage and the application temperature in order to give you an expected lifetime of these parts. So what you see here is we've taken the inverse power law in order to give you the acceleration factor for voltage, and we've taken the Arrhenius equation to give you the acceleration factor for temperature, and we've multiplied those two together to get you an overall acceleration factor. And then we've taken that and multiplied it by the life that's specified in the data sheet. And that should give you an expected lifetime at your application voltage and temperature. So when we look at the data sheet, for the example that we're going to use on the next slide, we're looking at KEMET's T520 series, which has a time of 2,000 hours, or a test time of 2,000 hours at 105 degrees C. And what we see is that for leakage, as long as it's within 1.25 times its initial limit, it's still essentially a capacitor within its specification. We do have other specifications, such as the change in capacitance, dissipation factor, and ESR. that we specify that the part should be within those ranges within its lifetime of 2,000 hours. But we just don't have the reliability model built for that yet. But I think that's something that we've been working on. But for leakage, what we see is that at its rated voltage and at its rated temperature, we have a part that's rated 2,000 hours. Again, this is KEMET's T520 series. So its rated temperature is 125, and then whatever its rated voltage is, or not 125, 105. Which is 0.2 years. And what we see is as we begin to derate the temperature, the life is going to increase up to, let's say, 45 degrees C. The life is going to be 752 years. And then the same is the case when we derate the voltage. When we begin derating the voltage, by the way, our recommended derating for voltage is anywhere between 10 and 20% for polymers or 50% for MnO2s. What we see is that the life is going to increase. So if we're using the part at half its rated voltage, it's almost 15,000 years. But when we start combining deratings of temperature and voltage, we start seeing a very, very large or high increase in what the reliability of this part's going to be. And that's why these parts last longer than generally anything else on the board. Because when you derate them, whether it's temperature or voltage or both, we're going to be getting a part that could last much longer. Now, looking at some of the strengths and weaknesses of the dielectrics, the top graphs are comparing to other technologies, the ECAP being in the green color, while the MLCC is in orange. We see that it has a capacitance retention over voltage, or the DC biased effect, or temperature coefficient of, or voltage coefficient of capacitance. We also have capacitance retention over temperature. ECAPs and MLCCs don't fare too well with that. Also, capacitance over time is stable. Most MLCCs class 2 and 3 have aging, and electrolytics begin to lose capacitance over time as well. And then when we're looking at capacitance over frequency, again, the capacitance roll-off frequency is around a megahertz or a little bit less than a megahertz. So it could be used at higher frequencies than ECAPs, but when you compare it to MLCCs, it does have a higher capacitance. Also, looking at the capacitance delivered, it is the most volumetrically efficient device. So you could use one tantalum capacitor in place of multiple MLCCs. Looking at derating, I said that the derating of the tantalum polymer is going to be 10 to 20%, while the MnO2 is going to be 50%. So on a 24-volt rail, you could actually use a 35-volt part as opposed to 50-volt MnO2s. It has a low profile. It also doesn't have flex cracking. It doesn't have the piezo noise or electrorestriction that an MLCC will have. It has a non-ignition failure mode. One of the problems with MnO2 is that it would burn up in circuits, and I could talk about this later if anyone has any questions. But the polymer does not have that issue. And then when you compare it to electrolytic capacitors, the polymer has very low ESR. So in turn, it has very high ripple current capabilities. And this slide, basically, I just wanted to kind of show or illustrate what the derating guidelines are. Depending on what the voltage rating is and what the reliability is, our recommended derating is anywhere from 10 to 20%. So if it's a 10-volt part, you would essentially be able to use it at 9 or 10 volts, up to 105 degrees C, and then additional derating after that. And then for MnO2, it's 50% with an additional derating up to 105 degrees C. So what that means for you is that you could use typically smaller polymers, because you could get the same CV or same capacitance with lower voltage ratings in this smaller case size, or you could just use a higher capacitance polymer in most cases in the same case size and the same voltages. Or you could get lower profiles. So there are a lot of benefits from going from the MnO2 to polymer. And just a quick comparison between the technologies, what you see for ESR versus frequency on the left is that the polymer is not only an order of magnitude lower in some cases in the ESR, but its change in ESR over temperature is very stable as compared to the tantalum MnO2. And then comparing the capacitance roll-off frequencies of the two devices, you'll see that the MnO2, because of its higher ESR, in general, it's going to have a lower capacitance roll-off frequency than the polymer. When should you not use polymer? There's a few applications or conditions. The first is frequency approaching 1 megahertz. The second is temperatures exceeding 150 degrees C. And we do have 150 degrees C polymers, and we're actually working on higher temperatures now. So this might be outdated within the next year or two. Anything over 48 volt rels, probably shouldn't use them as well, because these parts are only rated up to, I think, around 63 volts might be our highest rated voltage. So high voltage designs are out of the case right now, but that's probably something that we're going to, continue to add on to. Anything that's lower than ESR of 4 milliohms, we're also probably not going to want to look at a polymer. Typically with an ESR that low, you would need to look at an MLCC. Going back to one of the first slides where I talked about this is a polarized device. It cannot handle the reverse bias, so you shouldn't use this in a reverse biased application. Also, due to the way that we make the parts, low capacitances are also hard to achieve. If you need low capacitances lower than 0.68 microfarads, you probably need to use ceramic. And then whenever your device is connected to a battery, you're probably not going to want to use these as well, because due to the faults in the dielectric, they do have high leakage current, and they do have higher leakage current than MnO2s. So if you're switching over to from an MnO2 to a polymer, you need to consider the leakage current as well if it's connected to a battery. Now, moving on to our last slide, which is the product alignment or market alignment portfolio for polymers. We have a few different segments that we feature, that we target, which is the consumer electronics, telecom, automotive, industrial, and defense and aerospace. Each of these, we have our own product lineup, which you could find on kemet.com. But some of the things that have been influenced us, or the things that we have been focusing on for the products, are for consumer electronics. We've been pushing for smaller and smaller case sizes. I think right now we have a polymer that's equivalent to an 0805 MLCC. So these polymers are getting very small. For telecom, we're looking for extended life or high CV, which in a lot of cases, that's going to be the face down series. For automotive, we're looking for essentially the higher temperatures, the 125s, the 150 degrees C, and then additional ratings beyond that. We're looking for smaller case sizes as well. For industrial, we're looking for higher voltage ranges, and that's where we're pushing the higher voltages up to 75 volts. And then for aerospace and defense, we actually do have 75 and I believe 100 volt parts in our polymer hermetic sealed part. But for the typical surface mountable packages, those higher voltages aren't available just yet. But what we focus on is high reliability components, and that's going to be KEMET's T540 series, 41 series, as well as our new mil spec which should be coming out within the next year or so. And then we're also focused on 85-85 capabilities, which is 85 degrees C at 85% relative humidity. So we're looking for very reliable and robust designs for those defense and aerospace customers. So with that, I know we're 5 minutes over. We'll go ahead and end the meeting here, or the webinar here. And David, you go ahead and begin asking any questions.
All right, thank you, Sam, very much for this presentation. And we did get a request for contact information for you and Yekaterina, so we will provide that directly to the person who requested the information.
Okay.
But we also have another question here that says, why are you not recommending tantalums for frequencies approaching or exceeding 1 megahertz? How about a combination of tantalum and ceramic capacitors?
Yeah, so this goes back to the RC ladder effect, where the higher resistances are going to cause some of the tantalum particles at the end of or that are further away from the tantalum wire to start dropping off at those higher frequencies, which means you're going to have a large drop in capacitance as you're approaching those higher frequencies. When you're at the lower frequency, the RC time constant for some of those higher frequency, or not higher frequencies, but particles that are further away from the tantalum wire is going to be lower than the time constant for whatever frequency you're at. But as that frequency starts to increase, those RC time constants are going to continuously increase due to the increase in resistance. As I mentioned earlier, the resistance is going to increase with frequency, and that's the resistance of pretty much anything is going to increase with the frequency. But once it gets to a certain point, you're going to start losing some of those interconnected particles that are further away from the tantalum wire. And that's why we don't recommend using, or that's why you really can't use tantalum at frequencies above a megahertz. Some of them start rolling off lower than a megahertz, or most of them do start rolling off at lower than a megahertz. But as you're increasing the ESR, the lower that frequency is going to be. So it could be around 100,000 hertz or so. It could be 100 kilohertz. So it depends on the ESR of the device and depends on the capacitance and how much further away those interconnected particles are away from that tantalum wire. And I guess to answer the second part of that question, which sounds like decoupling, yes, you can use, and we do recommend you using multiple types of components together for decoupling applications. So if you use KEMET's KSIM tool, you could actually simulate the combined impedances and ESRs of the devices. So if you take a tantalum part and a MLCC part and you have a target impedance and a target frequency, you could plot them in KSIM, combine the impedances, and see exactly if there are any peaks that are above your target impedance. And if there are, you could essentially change the device. You could put a couple of those in parallel and you could see a drop. But the key thing is that the tantalums are going to be used for the lower frequencies, and the MLCCs are going to be used typically for frequencies above a megahertz. So you would use those in conjunctions with one another. You could also use film capacitors, electrolytic capacitors. But the key thing is that the tantalum capacitor is going to be used for frequencies lower than a megahertz. So I hope that answers the question.
Yeah, it certainly does. The next question says, would you recommend polymer tantalum capacitors for DC link function in a 48 volt MHEV application?
For DC link, that's a good question. Typically, I would see aluminum electrolytics, I would see films, and I would see ceramics. For tantalum, that's a good question. I might have to talk to a few people and come back with an answer for that, because I don't typically see customers using tantalum for DC link. So I'll get your name, contact information, and I'll reach out to you with an answer on that.
Okay, there is another question that came through just a general chat that says, are there simulation models that include voltage and frequency sensitivity? Oh, yes. Okay, I think that you already answered that. Okay.
Yep.
With the KSIM tool?
Yep. So I'll just pull it up here. So on our website, we have what we call KSIM. It's a simulator. On KSIM, you could reach it by going to ksim.kemet.com, or if you're on kemet.com, under the menu bar, it'll say Design Tools, and you could click on KSIM. But we have a capacitor simulator where you could select a technology or enter a part number, and I'll just select a polymer T520, which is the series that we were talking about earlier. Let's do, I don't know, a 10 volt part actually, and do 68 microfarads. And what you see here is we have a simulation of the impedance and ESR over frequency. And actually, I'll add in another part just for the heck of it. Let's add in a tantalum MnO2, 10 volt. Just to see the two parts, you can see that the ESR is an order of magnitude higher. And you could also see, well, in general, you could see that the part's just a higher ESR. But what you see on the bottom hand side of the slide is that you could change the quantity of parts. So if I change this to 10, we're actually putting 10 of those in parallel. You could also change the bias. So 5 volts. Why is it not typing? 5 volts. And then you could also change the application temperature. And as you could see, this graph for the polymer began to change whenever I changed that. So I'll change this again to 25 degrees C. You can see that it changed again based off of that, and you can change each of these. But where the tool becomes beneficial, especially for decoupling, and I'll add in a ceramic, is that, let's see, I'll add in a C0G, 1 nanofarad. You could see that it has a higher self-resonating frequency, which means that it's going to have higher capacitance roll off, or it's going to essentially become an inductor at a higher frequency. And what we could do is we could hit this combined impedance here, and we could see that the black and gray lines are the target, or not the target, but the combined impedances and combined ESRs of the devices. And like I said, if you have a target frequency and target impedance, you could ensure using the MLCCs and the polymers or MnO2s, electrolytics films, whatever it may be, that your combined impedances are going to be below that target. And you could just go through and add in more of these in parallel to lower those impedances. Whenever I just put 100 of those C0Gs, the combined total impedance at these higher frequencies just dropped. You could also look at graphs such as capacitance, inductance over frequency. And again, you could change any of these parameters. You can look at current and voltage, and this graph's a little bit misleading. It's actually ripple current and ripple voltage. So you can see the ripple current, ripple voltage capabilities of the devices over frequencies. You could also select the SPICE model, and the SPICE model is only going to show for the tantalum part because it's the first one selected. You could also look at capacitance versus biased, and let me actually select a part that will have a biased, an X7R. So you can see that the X7R has a DC bias defect, and as you begin to apply voltage to the part, you're going to see a drop in capacitance. And then the final graph I'll show is the temperature rise versus ripple current. Again, you're going to see how much this part is going to rise in internal temperature based off of the ripple current passing through the device. We do have some other graphs that are being added, but they're not added for every part number, so I'm not going to show those, but those are going to be capacitance change versus temperature, as well as AC bias. But this tool is available for you guys. If you put in a part number, it'll also bring up the graphs, but you could go through and select different components based off of what you think you need and do simulations. And then you could go to the bottom and export it into a CSV file if you wanted it, the actual values to upload to your own system or to your own calculations. Also SPICE models, S2P files. You could download it as an image, or if you're working with someone else, you could share it with them as well. So that is available for you guys to design in these parts.
Okay, and another question that came asking about the playback of this webinar. Yes, it will be available in a few days' time. And if you signed up for the webinar, which obviously all of you have, you will receive an email when that recording and slides have become available online for you to view. The last question we have for today is, moisture concerns still have to be adhered to in a polymer cathode solid tantalums?
Yeah, so the tantalum polymer is going to be a MSL3, so you do need to worry about the moisture. And I think in the data sheet we should have under storage and handling, there should be some kind of description on how those parts should be stored and handled. They do come in, I guess, MSL bags or packaging. So I guess if you're storing them in those, you should be fine. But if you take them out, there are specific concerns. I think the biggest concern probably is going to be the solderability of the device. If they're left in too high of temperatures or too high of moistures, there's going to be an issue with solderability. But in general, I think tantalum polymers are going to not really enjoy, but they're going to be okay with a little bit of moisture. It's just when the moisture becomes too high and you put it through a reflow process, that moisture could possibly build up, expand, cause internal issues. So you do want to make sure prior to reflow that the part is keeping as much moisture out as possible. But the parts do themselves like moisture. Especially when you're looking at the parts in a vacuum. Whenever they're in a vacuum, they're drained of that moisture. They're going to have charging issues, which is the anomalous charge that I'm sure a lot of military grade customers are aware of. But in general, the polymer itself does like a little bit of moisture, but it is a part that is MSL3, and you can find more information on that in the data sheet.
Okay, so that concludes our presentation for today. Thank you once again to everyone who joined us today. We hope to see you next time. Until then, we wish you the best. Goodbye.
Thank you.